Hi everyone, good morning. This video is just about an example of Bode plot, and I'm going to show you how to solve this kind of question in Bode plot using calculation for each pole and also zero. Look at the example here. Find the Bode plot magnitude and phase angle plot for the transfer function given as Hs equal to 200, s plus 20 divided by s, 2s plus 1, s plus 40. Okay, so what we do first is we change it to j omega equal to 200 j omega plus 20 divided by j omega 2 j omega plus 1 j omega plus 40. Okay, we rearrange so that we can identify the pole and also the zero. Okay, so what we do here, at the denominator here, j omega is still j omega. So this 2 j omega, if you want to make it only j omega, so we divide by 0.5 plus 1, and this one is j omega divided by 40 plus 1. Okay, so this 1 divided by 0.5 is actually 2, right? Okay, so here will be 40, and at the numerator here, this one should be 200. Oops, sorry, 200, and this one j omega plus 20, we make it as j omega divided by 20 plus 1. Take out the 20 here. Okay, and we solve for this. This one you can cross, so this one will become 100 j omega plus 20, as you write, divide by 20 plus 1 divided by j omega divided by 0.5 plus 1, another pole here divided by 40 plus 1. So if we see here, we can identify pole and also zero from here. Okay, and also constant. This will be constant. This will be 0 at omega equal to 20. And this will be a pole at origin. Okay, because there is no denominator here. And this is pole at omega equal to 0.5. And this is pole at omega equal to 40. Okay, so we have identified that. So let me write again the equation here, the next page here. H j omega is equal to 100 j omega divided by 20 plus 1 j omega divided by 0.5 plus 1 j omega divided by 40 plus 1. Okay. We can identify one constant k at 20 log 100. Okay, the calculation in decibel, okay, in log, so it should be 20 log 100, so 40 dB. Okay, so there will be straight line which is 40 dB to show that there is a constant, okay, on the Bode plot, and 0 at omega equal to 20. So this 0, there will be line, straight line, and then it will be a ramp with gradient 20 dB over decade. So this is 0 at omega equal to 20, and then there will be pole at origin at omega equal to 1. So if there is a horizontal line as this, so there will be pole that cross omega equal to 1, and another one is two poles at omega equal to 0.5 and omega equal to 40. So it will be something like this at omega equal to 0.5 and something like this at omega. Okay, and the gradient here should be negative 20 dB over decade. Okay, so now we look at the first quarter frequency. It means that the frequency that there is a changes at the Bode plot. Okay. Frequencies here refers to the frequency that we have a pole and also zero. Okay, so let me circle the corner frequency here. Okay, this should be the corner frequency 20, 0.5 and also 40. Okay, so we start with the first frequency, corner frequency, which is 0.5. This is involved in the overall Bode plot. So the first corner frequency, which is at omega equal less than 0.5. Okay, so we calculate the magnitude for all of this equation at the equation that is involved in the Bode plot. Okay, so in other words, at the numerator we have to make it log. Okay, 20 log 100 here. Okay, which is the constant, and then because 20 here is not yet used, so we just minus the 20 log j omega. Okay, so in other words, at the numerator is all summation, and then when we want to perform the division here, when we do the log, we have to minus the denominator here. Okay, so h j omega dv is equal to 20 log k minus 20 log omega. Okay, so because this involve omega less than 0.5, so we only use constant here and also j omega here, which is the pole at origin, because the pole at origin starts when you start the graph, it's already start here. Okay, this pole at origin. Okay, but the line here should intercept at omega equal to 1. So we have this equation 20 log k, which we take from this 100 minus 20 log omega, okay, which corresponds to pole at origin. So when omega is less than 0.5, let's say we want to start the semi-log graph at omega equal to 0.1. Okay, so remember when we have this Bode plot, okay, let's say this is 10 power of 0, so this is 1. So we want to start our graph here at 10 power of negative 1, which is 0.1. Okay, so we put the value of this 0.1 in this omega, we replace it and we calculate. Okay, so when omega is equal to 0.1, we calculate the magnitude of the graph here of the Bode plot. H omega is equal to 20 log 100 minus 20 log 0.1. So we use a calculator, we calculate here, we will get 40 plus 20 dB equal to 60 dB. Okay, so this is when omega equal to 0.1. So why do we do this? Because we want to plot the exact values. Okay, you can also plot using the method that I have shown you before during lecture, okay, which we just draw, and then we just draw all the individuals plot here, and then we combine the plot. That one is okay. But let's say if you want to really calculate the original the exact values, okay, before this we when we want to combine the values, we just use our knowledge in terms of pole and zeros, right? So now we want to plot the exact values. For example, at 0.1 we plot at 60 dB. Okay, so this is one value that we need to plot at 0.1, 60 dB. Okay, then we move to 0.5. Okay, so at omega is exact at 0.5, we can take the value 0.5 here. So h j omega in dB is equal to 20 log 100 is 40. We have calculated before here. So 40 dB minus 20 log, and this omega will replace with 0.5, so it is equal to 46.02 dB. Okay, so after we plot at 0.1, we plot 60 dB, and at 0.5, we plot at 46.02 dB. Okay, so this is the second value that we plot. Okay, now we want to move at the next corner frequency, which is 20. So we want to plot at from omega less than, from omega 0.5 to omega 20. Okay, so what we have now here is at omega between 0.5 and 20, we put the value hj omega dB is equal to 40. Okay, now because it involves 0.5 but it's still less than 20, so we take this value as well. Okay, so the value that the component here that is involved in this calculation between omega between 0.5 and 20 is 100, which is a constant. Pole at origin, anything pole and zero at origin always involved in all the calculation. Okay, but for the frequency that is involved with the that is related to corner frequency, we only consider it when it is in between, or it is within the range. Okay, so now we take this component, the pole at omega equal to 0.5, so 40, which means the constant here, okay, 20 log 100, and we minus 20 log we minus 20 log omega, okay, 20 log omega, which is here, and then we minus another one, okay, this component, 20 log omega divide by 0.5. Okay, so this is the equation involved when omega is between 0.5 and also 20. Okay, and we can see that from here there is two pole here, and it means that when we want to draw the overall plot, that this plot should drop 2 times, means that the gradient should be negative 40 dB over decade. Okay, so no longer 20 dB over decade, so the gradient should be steeper and sharper, right? So now we want to put the value so that we know where to plot. So before this, we have plotted at omega equal to 0.5, which is at the start of this equation. Now we want to plot at the maximum of this range, which is 20. So we plot at omega equal to 20. J omega in dB is equal to, is the 100, 20 log 100 constant, minus 20 log 20, okay, because we put in the value omega is equal to 20, and then minus 20 log omega here we replace with 20 divided by 0.5. Okay, so use your calculator to calculate this, and then here we will get the exact value, which is negative 18.06 dB. Okay, so by calculating this exact value, so you know where to plot. Okay, instead of you when you combine, sometimes it's gonna be a bit confused, but it's still okay actually if you want to use the combination part. But for this particular equation, if you use the combination part, it will be a bit confusing in terms of crop here, and okay, you need to know, you need to have the knowledge. For example, like I said here, between omega between 0.5 and 20, the drop should be 40 dB over decade. Okay, you need to have that knowledge because there will be two poles here. Okay, however, when you calculate the exact value like this, you know that at omega equals to 20, you will plot at negative 86 dB at y-axis. Okay, now we want to plot at, we want to consider another corner frequency. So the next corner frequency here after 0.5 is 20. Okay, it's 20 because there will be changes at omega equal to 20. So we derive the equation between 20 and also the next corner frequency, which is 40. So at omega between 20 to 40, Hj omega in dB is equal to 40 minus 20 log omega, okay, which refers to the pole at origin, minus 20 log omega divided by 0.5. And because the 0 here is at the numerator, so we have to add. Okay, instead of minus, we have to add 20 log omega divided by 20. Okay, so we have the equation here for omega between 20 to 40. We have already plotted at omega equal to 20, so now we plot at omega equal to 40. Okay, so we have here Hj omega in dB is equal to 40 minus 20 log 40. We put in the value of 40 at omega here. Okay, replace that value. And then 20 log 40 divided by 0.5 plus 20 log 40 divided by 20. Okay, so you put in your calculator, you calculate, and then here you will get 24.08 dB. Okay, so this is another value that we plotted. We should plot at omega equal to 40. Okay, so now the next corner frequency is 40. So we want to plot at omega beyond 40 so that we know where we should end our plot. Okay, so we derive at the equation at omega bigger than 40. So at omega greater than 40, Hj omega in dB is equal to 40 minus 20 log omega. We derive the equation first. Minus 20 log omega divided by 0.5 plus 20 log omega divided by 20. And this time, because 40 is at the denominator, so we have to minus 20 log omega divided by 40. Okay, so now we put one value. Okay, let's say we want to end our plot at omega equal to 1000. Okay, because this is a semi-log graph, so we want to end the plot here at 1000 here. Okay, so at omega equal to 1000, we put the value, replace the value of omega. Hj omega in dB should be 40 minus 20 log 1000 minus 20 log 1000 divided by 0.5 and then plus 20 log 1000 divided by 20 minus 20 log 1000 divided by 40. Okay, so you put in the calculator, you will get negative 80 dB. So now we have the value to plot when omega is equal to 1000. Where to plot? Because we have the value for each of the magnitude at the corner frequency. Okay, so I have labeled here from 0.1 up until 1000 because I want to make my plot larger. So I want to label by axis here starting from 0 dB, and this is negative 10 dB, dB, 30 dB, dB. Okay, so you label this. Okay, and dB, 20 dB, dB, 40 dB. Okay. Plot. So first we have one constant. Okay, at omega equal to 40. Okay, so at 40 dB you draw a straight line. Okay, we draw a straight line. at 40 dB. So this represents the constant. Okay, so this is 40 dB, and then we have poles at origin that intercept omega equal to 1. Pole at origin. Okay, so omega equal to 1 is here. Okay, so it should intercept omega equal to 1 at 0 dB. So 1 dB before that, it should be at 20 dB. And sorry, 1 decade before that, it should be at 20 dB. 1 decade after that, should be at negative 20 dB. Okay, so it should be like, so the line should be like this. Okay. Then you just continue the line. Is a pole at origin. And the next one is 0 at omega equal to 20. Okay, pole at omega equal to 0.5 first. Okay, so pole at omega 0.5. So we have 0.1 here, 0.2, 0.3, 0.4, and 0.5. Okay, and 1 decade after 0.5 here is 5. So this is 1, 2, 3, 4, 5. So we have 5. 1 decade is at 20 dB. Drop at 20 dB. Before that it is 0. It means that it will not be calculated for plot. So you plot the overall. So this is pole at omega equal to 0.5. And the next one is 0 at omega equal to 20. Okay, the next plot. Okay, so we identify 20 here. This is 10. This is 20. So 20 should be here. And 1 decade after 20 is 200. This is 100. This is 200. So 200 should intercept at 20 dB. Okay, so before that it is 0, and after that will be RAM for 20 dB over decade. Okay, so this is 0 at omega equal to 20. And finally, the next plot is at omega equal to which color I want to take? Okay, sorry, this purple color. It is at omega equal to 40. So this is 20, 30, 40. 40 should be, okay, 1 decade after 20, 40 is 400. So 400 should intercept at negative 20 dB. Okay, because this is pole. And before that is 0. After that is pole. Okay, so if you see here, it is parallel. All the poles are parallel because it drops by negative 20 dB over decade. So this is pole at omega equal to 40. So we have all these individual plots, and when we want to combine, we have to consider the constant here and also the 0 at origin here. Pole at origin here. Okay, so because of that, we should start the plot with RAM also, because there is a pole here. However, instead of starting it at 20 dB, we have to consider 40 dB, so we have to start at 60 dB. So when you want to combine, this is when we can get confused. So that is why we have calculate just now all the calculations. So I'm going to put it here so that we know where to plot. Okay, values that we have calculated previously. So now we can plot easier for the overall plot. Okay, you can also use the combine method that I have shown you before. Okay, so you can try that at home. But for here, I'm going to show you the plot using the calculation that we made before. So at omega equal to 0.1, you should plot at 60 dB. So you plot 60 dB. And at omega equal to 0.5, you should plot at 46.02 dB. So this is 0.5, 0.5 is here. So 40 dB is here, 50 is here. So you estimate the 46 is around here. Okay, so it's around here. Okay, so you plot. So basically this is around 20 dB over decade as well. Okay. Okay, but if let's say you want to combine, okay, you just drag this you just drag this line here to 60 dB. Okay, so instead of plotting just a pole with 20 dB over decade, you have to stop at omega 0.5. Okay, and now at omega 0.5 we have already plotted, and at omega equal to 20 you have to plot at negative 18.06. So at omega equal to 20 is here, negative 20 dB is here, so you estimate it is slightly before negative 20 dB, so it should be here. Okay, here. So this is the plot. Oops, sorry. The plot, like I said before, this plot, okay, this one is 20 dB, it's negative 20 dB over decade. Okay, the drop. And however, for this gradient is negative 40 dB over decade because it is a combination of two poles at origin and also 0.5. Okay, so when we stop here at omega equal to, the next one is at omega equal to 40, we should plot at negative 24.08 dB. Okay, why? Because we have 0 here. So basically, pole plus 2 poles plus 0, it will result in pole. However, the pole should drop by 20 dB only. However, previously we have plot the pole drop that is dropped at negative 40 dB, right? So now the gradient should be not as steeper as this 40 dB. So at 40 we plot at negative 24. So negative 24 should be between negative 20 to 30, should be somewhere here. So here we plot the plot. Okay, so this one is actually only negative 20 dB over decade. Okay, keturunan or the gradient. Okay, so that's why I said when you want to combine, you can drag your rulers so that it is parallel. Okay, parallel with this plot. Okay, with this 20 dB plot. And then finally at omega equal to 100, there should be the magnitude should be negative 80 dB. Okay, so okay, I haven't drawn negative 80 dB here. It should be negative 80 dB. Negative 70. Okay, so at 1000 here, it should go to negative 80 dB, which is here. So now we plot another plot. Okay, so why the gradient has changed now? The gradient is negative 40 dB over decade. Why it is changed? Because if we see here, starting from negative 40, okay, negative 40 here, there are 3 poles, 1, 2, 3. However, one only 0. So if we use the logic here, 0 is up by 20 dB over decade, and poles is down by 20 dB over decade. So 20, 20, 20 is 60. So 20 up here minus 20 is 0. Minus another 20 is negative 20. And minus another 20 is negative 40. So the drop here should be negative 40 dB over decade. Okay, so we have our overall plot here. This red color is your overall plot. Okay, so when you calculate like this, it will be easier for you to actually plot the exact position on the Bode plot. Okay, however, normally during final exam, the question will be in terms of sketching. Okay, so for sketching, you can just drag your ruler, but you should know when you have to draw the gradient at negative 40 dB or 20 dB or horizontal. You should have the knowledge of that. Okay, so what you can do now at home is you can try to plot the overall plot, but not using this calculation, but using the combination, and you learn yourself, and you can match your answer with when you perform the calculation. Okay, so I think that's all for the video. During the next class, we're going to do some more exercises on Bode Plot. Okay, and also class activities on Bode Plot. Okay, all right. Thank you very much. That's all.